Ground fault circuit interrupters, or GFCIs, are designed to protect against electrical shocks by detecting imbalances in the current flowing through a circuit. When someone comes into contact with a live wire and a faulty electrical appliance or other object that is grounded, the GFCI will trip, cutting off power within milliseconds to prevent serious injury or death. The National Electrical Code, or NEC, has required GFCIs in all residential bedrooms since 2002. This requirement applies to new and existing homes and is enforced by local building and safety inspectors. Bedrooms are considered high-risk areas for electrical accidents due to the presence of electrical devices, such as hair dryers, curling irons, and bedside lamps. These devices can be plugged into outlets near water sources, such as sinks, increasing the risk of electrical shock. While some early GFCIs were prone to nuisance tripping, manufacturers have made significant improvements in recent years. Firstly, GFCIs now incorporate more advanced circuitry that better distinguishes between actual ground faults and normal surges or fluctuations in current. Secondly, some newer GFCIs offer adjustable sensitivity settings, allowing users to customize the device to minimize nuisance tripping. Thirdly, GFCIs now use advanced filtering techniques to ignore small, transient surges and spikes that can cause false tripping. As a result of these improvements, GFCIs installed in modern homes are generally reliable and less prone to nuisance tripping. However, it's important to note that GFCIs should be regularly tested, monthly, and replaced every 10 to 15 years to ensure they are functioning properly. Ground fault circuit interrupters are a crucial safety component to modern homes, particularly in bedrooms, where the risk of electrical shock can be elevated due to the presence of various electrical appliances and their proximity to potential water sources. GFCIs work by constantly monitoring the current flowing through a circuit. They are designed to detect any imbalance between the outgoing and incoming current. This imbalance, even as small as a few milliamps, indicates that current is leaking somewhere, potentially through a person who is in contact with a live wire. When a GFCI detects such an imbalance, it trips the circuit, cutting off the power almost instantaneously, typically within 20 to 30 milliseconds. This rapid response is critical in preventing serious electrical shocks, burns, or even electrocution. The implementation of GFCI requirements in residential bedrooms by the National Electrical Code in 2002 was a significant step in enhancing electrical safety standards. This requirement mandates the installation of GFCIs in all new and renovated bedrooms, ensuring that occupants are protected from potential electrical hazards. The NEC decision to include bedrooms in the GFCI requirement stems from the recognition that these spaces often contain a variety of electrical appliances that can pose a risk of electrical shock. These appliances may include lamps, phone chargers, computers, and personal care devices like hair dryers and curling irons. Many of these devices are frequently used near beds or other areas where people may be in direct contact with grounded surfaces, increasing the likelihood of electrical shock if a fault occurs. Furthermore, bedrooms can sometimes be located near bathrooms or have en-suite facilities, further increasing the risk of exposure to water, which significantly amplifies the danger of electrical shock. While early GFCIs were sometimes criticized for their tendency to trip unnecessarily, often referred to as nuisance tripping, modern GFCIs have been engineered to minimize these occurrences. Nuisance tripping typically happens when the GFCI mistakenly detects a ground fault due to minor fluctuations in the electrical current, even when there is no actual danger present. Over the years, manufacturers have made substantial advancements in GFCI technology to address this issue. One key improvement has been the development of more sophisticated circuitry that can better differentiate between genuine ground faults and harmless current fluctuations. These advanced circuits employ complex algorithms and filtering techniques to analyze the characteristics of the current flow, allowing them to accurately distinguish between a dangerous ground fault and a normal surge or spike in the electrical system. Another notable advancement in GFCI technology is the introduction of adjustable sensitivity settings. Some newer GFCI models now offer users the ability to customize the sensitivity level of the device. This feature allows homeowners to fine-tune the GFCI to the specific electrical environment, minimizing the likelihood of nuisance tripping while still providing adequate protection against electrical shock. For example, in an older home with slightly erratic wiring, reducing the sensitivity of the GFCI may help to prevent unnecessary trips. However, it is crucial to note that adjusting the sensitivity should be done with caution and only by qualified individuals who understand the electrical system and the implications of altering the GFCI settings. Advanced filtering techniques have also played a significant role in reducing nuisance tripping in modern GFCIs. These techniques involve the use of electronic filters that are designed to block or attenuate small, transient surges and spikes in the electrical current. By filtering out these minor disturbances, the GFCI is less likely to misinterpret them as ground faults and trigger a false trip. These filters are carefully engineered to allow genuine ground fault currents to pass through while blocking the unwanted noise that can cause nuisance tripping. Despite the improvements in GFCI technology, it is essential to remember that GFCIs are not foolproof and can still malfunction. Therefore, regular testing and maintenance are crucial to ensure that these devices are functioning correctly and providing the intended protection. The recommended testing procedure for GFCIs is to perform a test monthly using the test and reset buttons located on the device. This simple test verifies that the GFCI is able to detect a simulated ground fault and trip the circuit as designed. To perform the test, simply press the test button. The GFCI should immediately trip, cutting off power to the circuit. Then press the reset button to restore power. If the GFCI fails to trip when the test button is pressed, or if it cannot be reset, it should be replaced immediately. In addition to regular testing, GFCIs also have a limited lifespan and should be replaced periodically. The general recommendation is to replace GFCIs every 10 to 15 years, or sooner if they show any signs of damage or malfunction. Over time, the internal components of a GFCI can degrade due to exposure to moisture, temperature fluctuations, and electrical surges, reducing its ability to function effectively. Replacing GFCIs at the recommended intervals ensures that the electrical system remains protected by reliable and properly functioning devices. It is important to choose GFCIs that are certified by a reputable testing laboratory such as Underwriters Laboratories or UL. These certifications indicate that the device has been tested and meets the required safety standards. When installing GFCIs, it is essential to follow the manufacturer's instructions carefully and to ensure that the device is properly grounded. Improper installation can compromise the effectiveness of the GFCI and may even create additional electrical hazards. If you are not comfortable working with electricity, it is best to hire a qualified electrician to install or replace GFCIs in your home. In summary, ground fault circuit interrupters are a vital safety feature in residential bedrooms, providing protection against electrical shock. While early GFCIs were prone to nuisance tripping, modern devices have been significantly improved to minimize these occurrences. Regular testing and maintenance are essential to ensure that GFCIs are functioning properly and providing the intended level of protection. By understanding the rationale behind GFCI requirements and taking appropriate precautions, homeowners can create a safer electrical environment for themselves and their families. Remember to always prioritize safety when working with electricity and consult with a qualified electrician if you have any questions or concerns. The evolution of ground fault circuit interrupters has been a journey marked by significant technological advancements aimed at enhancing both safety and user experience. Initially, GFCIs were primarily focused on detecting ground faults and interrupting the circuit to prevent electrical shocks. However, as technology progressed, manufacturers began to address the issue of nuisance tripping, which was a common complaint among users. One of the early improvements in GFCI technology was the development of more sensitive current sensors. These sensors were designed to detect even the smallest imbalances in the current flow, allowing the GFCI to trip more quickly and effectively in the event of a ground fault. However, this increased sensitivity also made the devices more susceptible to nuisance tripping caused by minor fluctuations in the electrical current. To address the nuisance tripping issue, engineers began to explore different filtering techniques. These techniques involved using electronic filters to block or attenuate the transient surges and spikes in the current that could trigger false trips. The filters were designed to allow genuine ground fault currents to pass through while blocking the unwanted noise that could cause the GFCI to trip unnecessarily. As microprocessor technology advanced, manufacturers were able to incorporate more sophisticated algorithms into the GFCI circuitry. These algorithms could analyze the characteristics of the current flow in real time, distinguishing between dangerous ground faults and harmless current fluctuations. This allowed the GFCI to make more informed decisions about whether to trip the circuit, reducing the likelihood of nuisance tripping. Another important development in GFCI technology was the introduction of self-testing capabilities. Some newer GFCIs are equipped with internal circuitry that automatically tests the device's functionality on a regular basis. If the self-test detects a problem, the GFCI will indicate this by flashing a light or sounding an alarm, alerting the user to the need for replacement. This self-testing feature provides an added layer of safety and helps to ensure that the GFCI is always ready to protect against electrical shock. In addition to these technological advancements, there have also been improvements in the physical design of GFCIs. Modern GFCIs are often more compact and easier to install than their predecessors. They may also include features such as tamper-resistant outlets to prevent children from inserting objects into the slots. The National Electrical Code plays a crucial role in ensuring the safety of electrical installations, including the use of GFCIs. The NEC is a comprehensive set of standards that covers all aspects of electrical wiring and equipment. It is updated every 3 years to reflect the latest technological advancements and safety practices. The NEC requirements for GFCIs have evolved over time as technology has improved and new safety concerns have emerged. The code now mandates the use of GFCIs in a wide range of locations, including bathrooms, kitchens, outdoor areas, and of course bedrooms. The NEC also specifies the performance requirements for GFCIs, such as the maximum tripping time and the minimum ground fault current that must be detected. These requirements help to ensure that GFCIs provide adequate protection against electrical shock. Local building and safety inspectors are responsible for enforcing the NEC requirements. They review building plans, conduct inspections, and issue permits to ensure that electrical installations comply with the code. Homeowners can also play a role in ensuring electrical safety by following the NEC guidelines and by hiring qualified electricians to perform electrical work. It is important to note that GFCIs are not a substitute for proper electrical wiring and grounding. They are designed to provide an extra layer of protection in case of a fault, but they cannot prevent all electrical hazards. It is essential to have electrical systems inspected regularly by a qualified electrician to ensure that they are in good working order and that all wiring and grounding are properly installed. When selecting GFCIs for your home, it is important to choose devices that are certified by a reputable testing laboratory, such as UL. These certifications indicate that the GFCI has been tested and meets the required safety standards. You should also consider the specific features that you need, such as adjustable sensitivity settings or self-testing capabilities. The installation of GFCIs is a relatively straightforward process, but it is important to follow the manufacturer's instructions carefully. If you are not comfortable working with electricity, it is best to hire a qualified electrician to perform the installation.